So all three of the examples that we have done so far look, if they weren't already in the rational form that looks like 1 over, or a over 1 minus r, we were able to pretty quickly algebraically write them as a over 1 minus r. But we actually have a couple of useful properties of power series that allow us to expand the types of rational functions that we can write using this this infinite geometric sum process, okay? And that's that because we have a power series, which is just a polynomial, we could take the derivative of every single term or the antiderivative of every single term just using the power rule. So, for example, if this is my series here, so a sub n is some coefficient x to the nth power, and this is the expanded form. If I take the derivative of this series, I'm actually taking the derivative of what's on the inside, so the inside of this summation, which is a sub n is still just a coefficient, so then I have n times x to the n minus 1. Okay, the other thing that I can do is I can apply an integral, and this would go to infinity. So I can integrate a series by integrating every term on the inside, but again, instead of integrating every term on the inside, we can just integrate the power series notation or the summation notation of this series. So using and this would be then in terms of x. So then using the power rule, this becomes x to the n plus 1, and then we divide by the new exponent. So we can integrate the terms on the inside, or we can differentiate the terms on the inside and have new series. So what's useful about this is that if I have another series, like part D here, that looks similar to the infinite geometric sum, I can use the fact that it is the derivative of another series to help me write the power series. Okay, so this is equal to the derivative of 1 over 1 minus x, okay? And let's go ahead and verify that. That is, if I'm taking the derivative of 1 minus x to the negative first, I have negative 1, and then 1 minus x to the negative second, but then times negative 1. Those cancel. That's why I have a positive here, not a negative. Don't forget chain rule. Okay, so just to verify, this is the derivative of this. Okay, and then this is the infinite geometric sum. So that means I have the derivative of, and I'm replacing everything in the brackets, the derivative of the infinite geometric sum. So the sum of x to the nth. And then if I want to take the derivative of this, I can use what we just talked about up here. So this is equal to the sum, I left that blank on purpose, of n times x to the n minus 1. Now, we do need to change the index here because we now have x to the n minus 1. That would be 1 over x, which is not a part of a polynomial, so I can't start at 0 anymore, meaning that first term just kind of drops off, and I'm going to start at 1 instead. So this is my power series for this rational function. Okay, oh, and then the radius is 1. Okay, because we just have an x there. All right. For this one, I don't want to try and integrate with an x squared in the numerator, but remember that the x squared or anything in the numerator can just be part of a. So I'm going to consider this like x squared times 1 over 1 minus 2x squared. And then I want to know if this is my derivative for something else. So let's just start with 1 over 1 minus 2x and then take the derivative of that and see what we get. Okay, so derivative of 1 over 1 minus 2x. Okay, and so that's going to be, which is 1 minus 2x to the negative first. So that's going to be negative 1 over 1 minus 2x squared, and then times negative 2 from the chain rule. So that becomes plus 2. Okay, so then in order for this to be the derivative of this, I need to have a 2 in the numerator. So I'm going to multiply by 2 here and divide by 2 here. Okay, so now my a term is this, and then this is the derivative of this. And remember, is equals. So this I can write as x squared over 2 times the derivative of 1 over 1 minus 2, 2 over 1 minus 2x, okay? So this part right here is the derivative of, nope, sorry, that is a 1. This is the derivative of 1 over 1 minus 2x. Okay, so this I can write as a geometric series where my r is 2x. So I've got x squared over 2 times the sum from 0 to infinity of 2x to the nth, okay? And then since this does not have any n's on it, then as far as the variable in the for the index of the summation goes, I can move the x squared in and out because all of that is just coefficient stuff. So I can actually move this to the inside, and I can write this whole thing as the sum from 0 to infinity of, and so I've got 2 to the nth divided by 2 for a total of 2 to the n minus 1, and then x to the nth times x squared will be x to the n plus 2. Okay, and then for my radius, absolute value of 2x has to be less than 1, so my radius is 1/2. So natural log of x is not a rational function, but I can write it, hold on a second, there we go. I can write it using a rational function because I know that the derivative of natural log of x is 1 over x. Or in other words, the antiderivative of 1 over x would be natural log of x, okay? So I can say that this is the integral of 1 over x dx. And then this almost looks like the infinite geometric series, but I'm going to have to adjust it a little bit, and I can write it as the integral of 1 over, and then I can write this as 1 minus x, okay? So x is the same as 1 minus the whole quantity 1 minus x, meaning that this is in place of my r, okay? And so now this that's on the inside is in the form of the infinite geometric series, so I can write that as the integral of the sum of the a is just 1, and then r is 1 minus x, and that is raised to the nth. Okay, and I still have a dx here, so I'm replacing everything in that box with this right here. And then I can apply this integral onto this, and this is an indefinite integral. So antiderivative of this is going to give me the sum of, and then I'm going to add 1 to the exponent, so 1 minus x to the n plus 1, and I need to divide by n plus 1, but I also need a negative 1 in front of this because the antiderivative of this with the chain rule would have a negative 1 there because of, you know, the u prime right here. Okay, and then I have plus c at the end of that. Okay, and then this negative could also be moved to the front, which I'll simplify that in the next step. We do need to figure out what c can be. So to solve for c, pick an easy value that is inside the interval, okay? And so whatever our interval is, we do know that the center is going to be a point that's inside the interval. And so this is centered at, this is the same thing as x minus 1 if we factor a negative 1 out of that. Okay, so this is centered at positive 1, so I'm going to do if x equals 1. Okay, so if x is equal to 1, then we have that the natural log of x, so plugging 1 in, natural log of 1 is equal to the sum from 0 to infinity, and then plugging 1 in over here, I've got a negative 1, and then I also have 1 minus plugging 1 in for x is just 0. To the n plus 1 all over n plus 1. Well, this is now just 0, which is equal to 0. Oh, plus c. Plus c. So all of this is equal to 0. So c is equal to the natural log of 1, which is 0. Okay, so my final series is the sum of negative, let me write it this way, negative 1 over n plus 1 times 1 minus x to the n plus 1 from 0 to infinity.